about your FSCD submission. I don't know if you plan.
Yes, I will.
Yeah.
I mean, I plan to say a few words about it in the end, if there is time for that. I'm not sure if there's going to be time, but yeah. Okay, so recording started. So what is this about? So I did some. Okay, then I briefly talk about this paper because this is, in any case, the motivation for this university stuff. So I did one FSCD submission about basically just trying to model as many language features related to universe levels as possible. So just model like lots of universe features, including like all kinds of universe hierarchies and like kind of like any kind of ordinal bounded hierarchy. And actually it doesn't even have to be an ordinal, it can be any like set with a well-founded ordering, so, or hierarchy, and also like some cumulativity, and also internal type for levels, elimination principle.
Sorry, by ordinal bounded hierarchy, you mean that instead of just having natural numbers, you can have universes which are indexed by an ordinal? Or
I mean, the universe is indexed by ordinal numbers, such that we have an upper bound. So every level is below one concrete ordinal number.
Mm-hmm. So like you could have like a universe type omega. Like
yeah, exactly. So we could have omega, then it's the usual stuff in Martin-Löf type theory, or we can do a bit more like in the new Magda version, which doesn't only have omega, but it has omega plus omega, and it also works. And actually it works for any ordinal number, and we have cumulativity and internal type for levels with elimination principle in Agda. So in Agda we already have like a level which is set 0, but it's a bit weaker because it doesn't have a general elimination principle in Agda. So in Agda we only have like some built-in operations on levels, and we can construct levels, but there is no level elimination. And here I also give a model for this level elimination principle. And then using this, it is possible to model like a bunch of features like universe polymorphism. So universe polymorphism automatically falls out of having this ordinal bounded hierarchy and the internal type for levels, because we can just quantify over levels and level bounds using pi types. And we can also model something like a Cox type cumulativity. But we can model it by coercive cumulative subtyping. Like for example, if I have some A which is in set 0, then if I have coercive cumulative subtyping, then I can also say in the surface language that A is also in set 1. But actually, this just gets translated into a coercion in the underlying syntax. So I just say that I have some lift of A, which is in set 1. But this lift is not like in Agda, because it computes on every type former. So it always computes out of the way, and you do not have to write explicit liftings in the surface syntax. So this can be just inserted as like using some kind of elaboration algorithm. Okay, so the paper is about this, but it turns out that actually I just use induction recursion, which is not very complicated, and all of these universe features very easily fall out of just using one universe with induction recursion. And maybe I will get in the end of this kind of talk to this point, but in relation to this kind of stuff, I read some papers and some materials about like trying to add stronger universes to more Martin-Löf type theory. So kind of stronger universes in MLTP. And of course, we can always just say that we have like a countable hierarchy, and if it's not enough, then maybe add like an omega times omega, or even more. And we can play this game for a long time, and it is probably sufficient for most of the practical purposes. But if we really want to go beyond this kind of like boring game of adding more universes to some type theory, so the idea is that we should try to model some large cardinal axioms using type theoretic rules. And these can go like much beyond what we see here. So the induction recursion is also a form of a large cardinal axiom, which is actually fairly large. So we can see that all of these transfinite polymorphic universe features, so induction recursion is even stronger than all of these features. So this is the idea.
What is induction recursion actually? I mean, okay.
So by induction recursion, I mean the DBA-Setzer, the large induction recursion. So not the small induction recursion, but the kind of the proper induction recursion, which was in the finite axiomatization for induction recursion paper.
Mm-hmm.
So.
But this is still it's a special case of induction recursion. For example, in this universe paper, we needed this was just small induction recursion, but it was not, I think, an instance of the DBA-Setzer.
Yes. So.
Or
yes,
not obviously.
So I looked at that, and it is the case that you need to use some kind of weird double induction recursion, and indeed that is not covered by usual induction recursion, or it's not immediately obvious how to cover it. But I mean, I have some suspicion that maybe it should be covered, but this is just an intuition, because the normal induction recursion is so extremely powerful that I think that there really should be some way to encode the weird induction recursion using just the normal induction recursion.
Yeah, I think so too. Mm.
I mean, like just by looking at this FSCD paper that I wrote, I mean, it's very clear that the usual induction recursion is just extremely powerful.
Maybe it's inconsistent.
It's not inconsistent. So
how do you know?
In the induction recursion paper, like there are these models with large cardinals. Okay, so the point is to model some large cardinal axioms using type theoretic rules, but why do we want to do it? I mean, it's already enough for mathematics to have like countable universes, and we don't care about.
Sorry, but what do you mean it's not consistent? Yeah.
I mean, if you accept sub-large cardinal axioms, then
sure. I was just saying, you're saying it's not consistent. Okay.
But actually, I mean, induction recursion, I mean, it requires some cardinal axioms which are large. Mm-hmm. When we think about the usual set theory, but they are not that large when we think about the study of large cardinals. So if you look at Wikipedia, so these cardinals are just around like the bottom of the list. And there are like so much more crazy stuff in set theory and all kind of completely out of the world large cardinals, which are even a lot, even larger.
So if it's in Wikipedia, it must be consistent. I understand.
Yeah, but what I'm just saying is that the consistency of induction recursion requires a strong assumption. I mean, when we try to compare it to normal set theory, but not a strong assumption when we try to compare it to like set theory, like we are talking about set theory for the sake of set theory. So because then there are even crazier stuff if we are like in.
Well, I have got an even strong large cardinal axiom, which is that every large cardinal axiom in Wikipedia is true, right?
I'm not sure because Wikipedia also has some inconsistent large cardinals. Okay, and why do we want to do this? And I think like one motivation is that it's just very convenient. Like here, I'm already using some constructive large cardinal assumption in the form of induction recursion to do all of this modeling, and it's super convenient, and it's way more convenient to use this IR than just to try to use something directly in set theory. And so I think it's already like a good motivation, but then there is also like this thing that we care about, like predicative and constructive versions. So and I mean, we might care about like constructivity for its own sake, and we may also care about predicativity, but this is like very vague. I mean, philosophically, it's super vague, like what is predicative and what is impredicative. But I think a very good definition for predicative versus impredicative is that the former can be kind of analyzed in a meaningful way, but the latter, like the impredicative, is completely hopeless. So if we are talking about a predicative theory, then we have some hope that actually, like the strength of this theory can be summarized in an analytic, in a compact way, like using ordinal analysis. But in impredicative systems, this is completely hopeless, and no one knows how to do anything like that. So there is this value of predicativity, is that it seems to be a lot easier to do this kind of meta theory of predicative theories, because like as soon as we get impredicativity, then like the strength of the theory just shoots up into somewhere like beyond the horizon, and the only thing which we can do is just to try to like scrutinize the relative consistency of impredicative theories, or things like that, or basically the best thing we know about like how fast functions in an impredicative theory can grow is to write some kind of busy beaver function or do some kind of diagonal argument. So it's not an analytic thing anymore. It's more like a kind of a relative thing. And I think that's the value of doing predicative reasoning. Okay, so here I have just some kind of standard library, and let's start with some basic definitions. And the idea is to move like from weaker universes, so weaker universes to some kind of stronger universes, and the strongest is IR here. And yeah, so and then we have the assumption that the set zero universe is kind of the background thing. So we can also just view like set zero as type and EL in some ambient theory. So everything is embedded into set zero, And also we just use IR to simply define these some kind of extended universes going from the weaker versions to the stronger versions. Okay, so
just before I forget it, sorry, just, do you know what happens if you have IR for Z0 and for Z1?
So if you have IR for Z0 and Z1 as well?
Yeah.
I mean, I don't think anything interesting happens. I mean, it is definitely consistent.
Is it?
And it is stronger than just having a Z0 and Z1, but no IR in Z1. But I'm not sure exactly how, but it is consistent. So you can put IR into any universe. There is some limitation, but we will see like how we can make a universe with IR inconsistent. Okay. So this is just like families of sets. It's Z0, the usual thing, and then we have the morphisms of families. So if I have a U and EL, so I mean, often I will call the set U and the family EL if I want to talk about families which are also universes. So a morphism is just a function which goes from U to U prime and kind of it preserves the elements. Okay, and then we also have internal families. So this is an internal family when we already have a family, and inside the family we just have the notion of a family. So if you have a U and an EL, then we can just pick any A, which is a code in U, and then we can also have a function which goes from EL of A to U. So this is an internal notion of a family. And then sometimes we also want to talk about like what is so a set is contained in a family. So we have this set A, and then we have U, EL, and it just means that there is a code for A in U. So there is some A prime, which is a code in U such that the elements of A prime are exactly the same as A set. Here, of course, we could also have like a weaker thing here, like an ISO of sets, but it doesn't really matter in this file. Okay, and then we also have when is a family contained in a family.
Fair, but everything you do is consistent with univariance, I assume, no?
In this file, yes. So this is without K in this file.
Okay. Mm-hmm.
Okay, so and when is a family contained in a family? So now I call this family AB, and then I have a family which I just call U. So some family AB family is contained in the U. If A is contained in U, and moreover, for every element of A, BA is also contained in U. And then we have some notions which I didn't define in Nagda, but which are also interesting. So what is a universe? So a universe is just a family which is closed under basic type formers like NUT, phi, and so on. Okay, so whenever we have a family with basic type formers, it's a universe. And what's a subuniverse? So F is a subuniverse, or maybe U is a subuniverse of U prime if there is some family morphism from U to U prime. So it's just any function which maps codes to codes, and it preserves all the elements of the.
But should it not be? I mean, a subuniverse, I would think, should be injective on U and actually equality. What is on EL? I mean, that's what I would think of a subuniverse.
I mean it's. Yeah, but I don't think. I mean, I think it's enough for our purposes. I mean, if you take any code in U and you can embedded it, you can map it into U prime and you still get the same elements, then I'm not sure that it's that interesting to say that it's injective on quotes. Right.
Oh yes, you get okay. So in FAM morphism, you already assume.
Yeah,
okay,
it's somehow it's already injective. Yeah.
Yeah. It's not injective, but it's
Yeah.
a quality on EL.
Yes.
Yeah.
Yeah.
But you could identify. I mean, you still could identify. So like, if you have a universe which is not univalent, and then you have a univalent universe, where you obviously identify codes, you would still call this a subuniverse, yeah, which I wouldn't actually, to be honest. So it's actually has a name. It's called the univalent completion of a family, and univalent completion I wouldn't say is not a subuniverse, but anyway.
Okay. Okay, so here we have like another kind of subuniverse, which is the recursive subuniverse. So you have a family morphism when the mapping of codes preserves all the type formers. So if I do something like a mapping of a pi code A to B, then this is strictly the same as a pi code of an f of A and then some f of B. And this is going to be quite obviously injective. And usually this is like the stronger version which we are interested in.
So why is it injective?
I mean, if it preserves all like type codes, then it's necessarily injective. I mean, if we are not doing any crazy stuff like adding or quotienting the type of codes in some way.
It will be injective in the syntax, not in any model.
Yes. Okay, and then we also have the internal subuniverse, which is just an internal family in some universe, which is the subuniverse of U. So whenever I have something like a UEL, which is just a family, and then I can also have an internal family. So some kind of, let's call it small u, and small el is just an internal family over UEL. Then this small UEL can be just a subuniverse of this large thing, and so it can be a subuniverse because so every internal family can be interpreted into this family, and then we just say that the small UEL is a subuniverse of large UEL if like we interpret this into fam, and then that's a subfamily of this fam. Okay, so let's look at just very simple universes. So the simple universe is just closed under type formers, and in set theoretically, this is like having an inaccessible cardinal. So if alpha is zero inaccessible, if we take any smaller set, or if we are talking about ordinals, then we take any smaller ordinal beta, and then the power set is still smaller than alpha. So this is kind of like closed under power sets.
Hang on, power set to 2, do you mean bool or what? Yeah,
2 for bool.
Yeah, that's not powers. I mean, power set would be into prop.
Sorry. No.
No, that's right. It was right.
Yeah.
I mean, these are decidable power sets, which you write there.
I mean, here it's decidable power set, but in set theory, it would be the same as the usual power set.
Yeah.
And actually, it's a bit interesting because so in set theory, like we have that is the same as like power set of beta, and it's a bit funny that in type theory, if we have just a single universe, then it's a bit like having an inaccessible cardinal. But in set theory is already like super powerful, even if we do not assume that there is any inaccessible cardinal. So why is set theory so powerful even without having an inaccessible? And the reason is that excluded middle plus power sets is kind of impredicative.
Yeah, it is. Because 2 equals pop if you have lem.
Yeah, exactly. So if you have lem and power sets, it's already impredicative, and it explodes away from our ability to analyze already. Like there is no ordinal analysis of excluded middle together with power sets. But in type theory, I mean, if we are working without lem, then we can do this kind of leveling up into stronger theory in a more gradual way, which can be still analyzed in some sense. Okay, so this is just an inductive recursive definition of this universe, and like what do we gain if we have this kind of universe? So then what we gain is we can have like a large elimination, and we can also have like a polymorphic function over this small u. And if we do not have this, then we cannot do any large elimination. Or okay, so if we do not already assume large elimination, then with this we gain the ability to do large elimination, because then, I mean, if you imagine like the imaginary syntax of some type theory, then U would be just a type in gamma, and we would also have like EL. And because U is just a type, it is possible now to write a function which goes from any type to U. So we get large elimination, and we can also write now functions like A, which goes from U to whatever. So the question is, would the trivial family 1 arrow 1 also be considered a universe? So you mean that we have like the unit type, and the decoding just goes to the unit type?
It's closed under all type formers, no?
Yeah, I think
apart from plus, okay, plus, it's not closed under bool, no? But, I mean, it's not closed under bool, I think. So maybe type formers include bool.
Yes, I mean, it depends.
No, not really, because I mean, nut is not hard, no? I mean,
I don't think it works even for nut, because by saying that it is closed under natural numbers, then we mean that there is a code for nut, and also that the EL of nut is the same as the external natural numbers.
no.
So we also specify that the EL of codes is isomorphic or equal to the external type formers.
Sorry, I also have a question which I always wondered. How essential is induction recursion here? So if we don't have, if EL is not, I mean, if EL is, if there's no dependency, what do I mean? I define U first and then EL. So let's say we have a simply typed universe where yeah, where if I have A and B, I get A arrow B. So then I don't need induction recursion. But is this universe really weaker than this universe?
I think it is. It is weaker. So if I
mean, it contains basically everything which is in there, but not with the same precision, right?
So if I have a simply typed universe, then this does not have to refer to EL. Right. Then it also works if I just say that I have this as an inductive type, and if I also have large elimination.
Yes, that's the point.
And I can define EL.
Yeah. But the large eliminations seem to be the main source of power here, no?
I'm not sure about this question. And okay. Maybe, so you say that if you have large elimination and inductive times, then it's as powerful as having, or it could be as powerful as having.
Yeah, it was a question, right? Yeah.
I don't know
the answer. Yeah,
I don't know.
Okay.
Okay, so let's continue. So the next thing is a Gröthendieck universe. So if I have some universe which is UEL, which is Gröthendieck, then I know that if I take any type code, so if any code which is in the universe, so then it is also contained in an internal subuniverse of U. So it's a bit like the set theoretic Gröthendieck axiom, but in a type theoretic way. So if I take anything like any type which is in the universe, I can find a subuniverse such that it contains that type. And but it is very important to say that it is an internal subuniverse because, of course, everything in the universe is already contained in some universe because it's contained in the universe. But then the point is that it should be an internal subuniverse. And UEL is not an internal subuniverse of UEL. It's it's like a smaller equal, but only in an external sense, but not in an internal sense. And then this is a bit like one inaccessible in set theory, because like if alpha is this Gröthendieck universe, then it's one inaccessible if, well, it's zero inaccessible, and then for every beta which is smaller than alpha, there is always a zero inaccessible gamma, which is between beta and alpha. So you can take any ordinal which is smaller than alpha, and you are able to find a zero inaccessible ordinal which is still smaller than alpha. Okay, and how do we define it? And using induction recursion, the way we define it is that first we define, so this is called the universe operator, and this is just a module which is parameterized by some given set. So we say that for every U which is a set, we have this inductive recursive definition. So we have this small u, and then we have this small el, and here you can see that the small u is closed under the basic type formers. So it's closed under natural numbers and pi, and it also has this u prime which is a code, and the code stands for this given set. And then in EL, well, of course, natural numbers becomes natural numbers, pi becomes pi, and the code for u becomes the given u. Okay, so first we define this universe operator, and then we define the Gröthendieck universe. So this one is the Gröthendieck u. And then the way it works is that, of course, once again, closed under the usual type formers, but we have this small u prime, and the way the small u prime works is that so whenever we have like anything in u, then the u prime of A yields a subuniverse, so it yields an internal subuniverse of u. And we can see it in the EL. So if I want to do an EL of a u prime of A, then I just use the small u, which is the universe operator on EL of A. And But at this point, I still have to prove that actually we get the internal subuniverse, and in this case, it is actually a recursive internal subuniverse. So what I have to prove is that whenever I have something in this U of EL of A, then I also get a code in just U. So by using this small U prime, I get subuniverses, but it can be embedded into the large universe still. So I just define these functions here by recursion. So basically every code, like the code for natural numbers is mapped to natural numbers, pi is mapped to pi, and the U prime is mapped to some given code. So this A is like U. So if we go back here, I mean, all of these kind of universes can be a bit confusing. So we have to look at it a bit, but I will just try to summarize like what kind of features and properties we get as we move to stronger and stronger universes. So you can see that the universe operator already has a way to refer back to this parameter, and we can just use this parameter to interpret a code with an external, like a code in the larger U universe. And we also have to prove that this embedding preserves elements, so we can prove that in a mutual way. And there is actually a simpler way to define these subuniverses, is not by doing a recursion, but just by saying that, okay, we have this as a constructor, as an inductive constructor in the syntax of this Gröthendieck universe, and then it also works, but it's not a recursive subuniverse anymore, but it's more like it's an inductive subuniverse.
But don't you need an equation then or something? I mean, don't you need an equation for EL prime?
For EL prime, so the equation is really, I mean, it immediately follows. So
oh, I see. It's just A. Okay. It's just A. Okay.
And just let me just comment this stuff out, and I will comment it back. Then, right, so I have this EL, then I can just use the EL of the universe operator, and then it, by definition, this holds that this is a subuniverse.
Okay.
Right, so it's very often, it is much easier to have an inductive subuniverse than to have a recursive subuniverse, but the recursive subuniverse behaves a bit more nicely because there is no duplication of codes of types.
But are there, if you do it inductively, is it still true up to isomorphism?
So if you do it inductively, then the subuniverse embedding preserves ELs strictly still. So because like if we go back here, so we have that so in a subuniverse the ELs have to be preserved strictly, and it also works if I just do this embedding in an inductive way, because I can just define this EL and the EL prime by induction recursion to be the right thing. Okay, but let's go back to this recursive definition now.
You need to get rid of EL prime as well, or comment it out at least.
Yeah, I just But I mean, sometimes it's not a problem to have. I mean, the difference between a recursive and a non-recursive subuniverse, it doesn't matter. But when I try to model my type theory, then it really matters, because having a recursive subuniverse. So in model of TT, So the recursive sub-U, it corresponds to a lifting operation which preserves all the type formers, and that's something which I usually want to have. So in my model of TT, I really want to have recursive subuniverses, but here it's not so important. So the question, is an internal subuniverse a subuniverse? Yes. So you can take any internal subuniverse and just interpret it as a... So you take any internal family and just interpret it as a fun, like an external fun, and then it will be a subuniverse of the larger universe. Okay, so what do we get from this setup? So we get that if I start with any type, and then I can create a new subuniverse using U prime. So we get like a U prime M prime is a subuniverse of the large U, and then the U prime of M prime is a subuniverse, and so on. So what we get essentially like a bunch of subuniverses, but the subuniverses are not subuniverses of each other. So this is quite limited, because what we can do is that we can do like a universe polymorphism in the big U over all kind of like this iterated small U primes like this. So we can do a universe polymorphism in the big U, but instead any of these small universes we cannot really reason. Cannot really have polymorphism over all other U prime universes. So it's kind of a flattened hierarchy, because on the bottom, like we have some U, whatever, we can define this like by recursion on natural numbers. And we know that on the top we have U, but we do not have like an interesting relation between all of these bottom universes. And here I do some...
So hang on, why not? Hasn't U1 a symbol for U0? Yes, it does, no?
Yeah, so U1, okay, we can look at an example. So you can see here that U1 is defined as U prime of U0. And indeed, so this has a symbol for U0.
Okay.
But what happens if I want to write a polymorphic function type which lives in U1? So I just let's call it fun, and fun is something which is an EL of U1. So an element of U1 is just a type code, right? And then I write a phi prime. Okay, and here I can just refer to U0 by writing U prime. But now I have an issue, and the issue is that there is no way to do anything interesting with A here. I mean, I cannot create a code in U1 out of a code in U0.
Well, you don't have an embedding from U0 to U1. Right?
Yeah, I do not have an embedding. I mean, in U1, I can still write functions which operate on codes in U0. So here I have some example. So if I'm in U1, I can still write a function which goes from U0 to U0. So this is a function type U0. So what I do not have is an EL which creates a U1 code from a U0 code. So that's why I cannot do any polymorphism.
But hang on, recursively you can define this, no? I mean, you can just map all the... Oh, because you don't know whether... if your universe is of initial in a way, okay. If you have universe recursion for U0, then you could just define this by recursion, right? But you're not assuming...
No. So here, that's what I try to do here. So here, we try to do an embedding from U0 to U1.
Huh?
And you can see, so here I declare this function which goes from EL of U0 to EL of U1, and then I also have to show that it preserves the elements. And okay, so this is straightforward. So n prime is mapped to n prime, and pi prime is mapped to pi prime. But here I have an issue because this U prime is a code for the natural numbers, but in U1 this is a code for U0, right? So it does not preserve, so this mapping does not preserve the elements. And if I go into this hole, you can see my goal is the natural numbers should be equal to U of natural numbers. So the problem is that in U1, U0 is represented, but so in U successor of n, U suc n is represented with the code, but the elements are not represented.
Okay.
Okay, so this was. So the question is, could you replace U with something that takes a family rather than just a type? So that's exactly the idea of the next step. The next step is when we have a superuniverse. So this comes from Palmgren. And we say that U. So we say that U is a superuniverse if every internal family, but my notation is a bit inconsistent. So U is a superuniverse if every internal family is contained in an internal subuniverse of U. So now we do not have this closure under just so we extend exactly as Paulo says, we have this closure property, but for families and not just for simple types. And now this is a lot more powerful because whenever we have an internal family like this F, we can send it to, I'm just calling here informally, like reflect F is going to be again an internal family, which is also a subuniverse of U. And then we can do this in an iterated way. So if I say that reflect of F, then this is also an internal subuniverse. But unlike previously, now I also know that reflect F is a subuniverse of reflect F, which is again a subuniverse of reflect F. So by doing this iterated family reflection, we always get a cumulative hierarchy. And if we have infinitary types in U, this means that we get transfinite cumulative hierarchy. Yeah, and I mean not just one hierarchy, but for every kind of infinitary, like any kind of transfinite hierarchy, which we can express in the big U, we can always just define a cumulative hierarchy internal to the superuniverse. Okay, so yeah, so here we have again like this universe operator, and then we get a family. So everything is parameterized by a family, and again we have the small u and the small en, which is close under the usual type formers. But also we have a code for the big U, and also we have a code for the big EL, which we get as parameters. And you can see that U prime is just U, and EL prime is just interpreted as EL. Okay, and then we define the superuniverse, and now I do not bother with trying to make this like recursive subuniverses. I just do it inductively. So I say that I have the usual type formers, and then I have kind of the reflection, like the first component of this reflection. So if I have like this reflect, which goes from an internal family in U to another internal family in U, we can just unfold this this principle by saying that I have the first component which goes from an internal family to just something in U, and then I have an EL prime which goes from first I get an internal family, and then I get an element of U prime of that internal family, and then again I get something in U. And so in the comment I wrote that this is not inductive actually. So you can see that I have U prime here, and in the type of EL prime I have once again U prime, but this can be just unfolded into a non-inductive definition, because here in EL I can just take the definition of U prime and just inline it into this thing here. So this is still just a normal inductive recursive definition.
Mm-hmm.
Okay, and and now we can define a cumulative countable hierarchy in the superuniverse. So I can say that maybe there is, let's call it UM, or maybe UM, which goes from not to U, and then UM of 0 is just can be anything. Okay, actually there is a slightly more convenient way to define it. So the slightly more convenient way to define it is the following: is that I say that here I already have the U prime, and then I just define kind of by mutual recursion, but which is also non-essential, another UN, and let's call it UN down, which goes from and this is UN down 10, and UN down 0 is should be just natural numbers, and this is UN. Okay, I will also write the more direct definition out, because this is some kind of optimized definition which is more easy to use in examples, but maybe a bit harder to understand. Yes, and I also need an EL, small EL, just like RLN. Yeah, should this be? Okay, let's just write the simpler version, because I kind of lost what's happening here. Just let's do it the simple way. And because we want everything in here to be a universe, then already here I have to write a U prime, and then maybe this could be U prime of N prime. So that's why I try to kind of merge this definition, because I already know that everything here has to be a U prime. So I don't want to pattern match on 0 and suck to know that this is a subuniverse, right? So and this is just constantly natural numbers, and here I can do like a UN of n, and yeah, let's have to define here. This is an ELN. And here I have to pattern match on this n. So ELN of A is just sorry, what's happening here? So I already did this in another file. So from an element, I want to get a U. So I just do it recursively. So for 0, I have this, and the elements of this should be just this EL. No, I'm stupid. It's just an EL prime of A. So the EL prime of what's happening here? Yeah. And here this is the ELN. And this is also just a mere prime of A. Okay, I have this. Just give me one moment. I have this in another file, which is a bit more usable. Probably I just made something more complicated than strictly necessary. Mm-hmm. Oh, right. Yeah, so in the other file, I just so instead of doing this direct definition, which is a bit cumbersome, so what I did was to define this U hat like this kind of a reflection, so that if I have a fem I of UEL, then I can just return this fem I of UEL. So maybe yeah, and then this is a U prime of AB, and this is an E prime of A. Okay, and now I can just define this UN by recursion. So what did I do here? Yeah, so here I just gave the natural numbers and the constant natural numbers family, and here I gave the U hat of the UN of M. Okay, and this gives me a kind of cumulative countable universes. And then I'm also able to define some codes for transfinite universes, because I can take like the sum of all of the UNs and get some type which is already included in the super universe. So I can define the U omega, which is also included in the super universe, and just do it by saying that I take the U prime.
Mm-hmm.
But here I would also I need a sigma type, but we just assume that there is a sigma type. So I just take the sum of all, like for all natural numbers, I just pick a natural number and then pick like a code in some UN universe for every n. And then decoding is very simple because I just use the decoding function for the particular n in the hierarchy. Okay, so that's the super universes, and let's move on. So we could also do something like just define some Brouwer ordinals with like a 0 and has a successor which goes from O to O, and it also has a limit which goes like this, and then we could also define by recursion on this O type some universe hierarchy in the super universe. And whenever we take a limit, we just take the countable union of all of the previous universes. Okay, so what's the next thing? So the next is the Mallow universe. So the universe, like the U here, is Mallow if we have that every family operator. So now, if we pick any function which goes from which maps an internal family to another internal family in U, there is an internal subuniverse of U which is closed under F. So it means that there is some reflect which goes from this to this, such that if I take any like a G which is an internal family in U, then yeah. So if I take any G which is an internal family MU, and I also know that G is contained in reflect F, then I also know that that FG is contained in reflect F. So what this means is that like any way that you can map an internal family to another internal family, there is some subuniverse which closed under this operation on internal families. So like no matter how you try to invent some new function which goes from a fami to a fami, there is some universe which is closed under it. So like from every internal family operator, there is some universe such that you cannot escape from that universe using that operator. Yeah. Okay, I just wrote this note like what is this set theoretically? So set theoretically, just let's not dwell on it, but it's kind of fun. So I previously mentioned like the universe is inaccessible, and the Gröthendieck universe is a one inaccessible, and then we can define the alpha inaccessible by saying that so K is an is an alpha inaccessible if for every beta which is smaller than alpha, like B inaccessible are unbounded below K. And then we can try to like take this further. So we can do a hyper 0 inaccessible when K is K inaccessible, then a hyper 1 inaccessible, hyper, then a hyper to the power of alpha inaccessible. And then we can get to the Mallow cardinal. And K is a Mallow cardinal if it's hyper to the power of K inaccessible. So this is like quite strong from the perspective of normal type theory, but as I mentioned, like compared to other large cardinal axioms, it's still not very large. And unfortunately, I haven't written any formalization here, but you can imagine that that it's possible to still define a Mallow universe using plain induction recursion, but we have to care about one thing, and is that if you look at the type of reflect, then it's not a strictly positive so because here you can see that there is some kind of negative magic going on in the type of reflect. So it means that a Mallow universe cannot be inductively defined, or a Mallow universe is not inductive, so it does not support induction on type codes.
Mm-hmm.
But
so sorry, what happens if we switch off? I mean, can we not define a universe now? We just switch off the positivity checker, or do we get something inconsistent already then? Or?
So in Agda we can already we cannot define a new Mallow universe, but we can show that set 0 is already Mallow.
Mm-hmm.
So in Agda we already have that set I supports IR. Therefore, set I is Mallow universe. But here what happens is that we just show that set is Mallow by defining like this kind of parameterized data type. Like so we define the universe operator for this reflection principle inside set, but we cannot do induction on set itself.
But is it? I mean, I think I had that this is inconsistent if you had a Mallow universe with induction. Is this correct? I mean, I vaguely remember Tony saying something.
Mallow universe is inconsistent with induction on type codes.
Huh?
So you cannot have a universe which supports induction on the type codes and which is also Mallow. But you can have a Mallow universe which is just like the usual parametric universe when you don't have a type case operation.
And why is it inconsistent? Is there a way to see this easily? I mean,
I can give a very simplified example. So like a very simplified example, which I just created a bug report in Idris 2. So when I was looking at these Mallow universes, I thought about like, then does this mean that Idris 2 is inconsistent because Idris 2 has type case operation and induction recursion at the same time? And it turns out, yes, it is the case. Idris 2 is inconsistent because of this. But we can give like a much simpler example. I mean, in Idris 2, we can say that there is.
Interesting. That's interesting because it's not inconsistent because there is some like oversight, but it's inconsistent for foundational reasons. Right?
Yeah. So in Idris 2, I can just define a fan which goes from. So in Idris 2, the universe is called type, and then I can just define a function by this type case operation, which goes from a type to a type, and I say that for a fan of f, this is just an f, and for everything else, this is just the identity function.
Mm-hmm.
And then you can already see that what I have just defined is the untyped lambda calculus. So I can define some omega, which is type, and then omega is maybe, I just define the looping combinator in untyped lambda calculus.
So hang on, this fun is just, can you do this in Agda or why not? Oh, you cannot do the type case in Agda.
I mean, I cannot do the type case in Agda.
Yeah. But so fun is just, has no constructors, right? It's just.
Yeah, it's just, I only care about the type code.
You just introduce a new type symbol, fun, okay.
Yes.
Oh, okay. Oh, yes. Well, seems, yeah.
Yeah, so this is the limitation. So if you have induction and recursion, you cannot have type case at the same time.
Uh-huh. Hang on, but there is a form of type case. Hang on, we could have type case, which is stable under univalence, which this one obviously isn't. That should be harmless then, no? Because fun of f is just the empty type, right? So.
I mean, I'm not sure. I mean, of course, there can be many universes which support type case, but they have to be weaker universes than Mahlo.
Yeah, no, I wonder, is it this is type case? I mean, as I say, type case is inconsistent with univalence, right? But you can specify that you want to have a univalent universe where all the codes are somehow reachable, right? By basically saying you have a type case which is stable under univalence, right?
Yes, I think that works, but that universe, I don't think. I mean, I think it has to be weaker than a Mallow universe because
I think this is not Mahlo.
It's definitely not Mallow. It's just basically. So what I've seen something like this from Mike Schulman from a while ago, when you have this univalent inductive recursive universe.
Yeah.
But it's more like it's just a simpler universe, right?
Yeah, but we could also. I mean, we could have it. I mean, we could have a constructor for IR. Right? We have an explicit type constructor for IR, right? So, but maybe IR is always non-univalent. I don't know. I wonder.
Yeah, I also don't know. Okay. Yeah. So
Paolo is asking a question.
So where
have
I
this is just a simplified.
I have not used IR, so this is just some naive type case thing. It is true that IR is inconsistent with type case, but it is also true that IR is inconsistent with this very simple stuff, and you just have type parameters like which are not completely, which are not strictly positive. So.
Hang on, this is a type case. Sorry, Paolo is right. So type case is inconsistent here. Right?
Yeah, so type case is inconsistent if you have any type former which is not strictly positive in type itself.
Yes.
And if you have IR, then you have that clearly. But I mean, you don't need IR. It's a inconsistent way before you have IR.
Yeah. So, but then the Idris 2 bug is that it has type case, or what?
I mean, yes, you can say that. But I think, I mean, this could be repaired by saying that there should be a positivity checking for type formers, and you can only do type case strictly positive type formers.
But it's a bit, I mean, you can certainly introduce this type which is parameterized by a.
Yeah, I mean, you should be able to introduce it, but what I say is that the Idris totality checker should flag a pattern matching on a non-strictly positive type former.
Yeah.
As non-terminating.
Sure. Okay, fair enough. But then, hang on, is this basically the reason also why Mahlo is inconsistent with induction? Yeah, can you explain this again? Okay.
Okay, so Mallow is
okay. Now I understand. Sorry, can I try? So because you say you have this operation, this Mahlo operation there, and the Mahlo operation itself is exactly of this form of your fun, right?
Yeah, I mean, so this reflection, this operation reflection principle in the Mallow universe, it is negative recursive if you write it as an inductive construction.
Yeah. So then but reflect is not a constructor, but there is some constructor which needs to be negative, right? And then if you do a case on this constructor, you exactly have this.
Yes.
This 2-bug. Okay.
Yes. So what we can say is that we do not have an induction principle for the Mallow universe. We can still use reflect as a way to construct a new element of the universe, but we cannot inductively go into like this reflect thing.
So is there maybe also a way to weaken reflect that it becomes less harmful somehow?
Yeah, I mean, like you can see that the super universe is still compatible with induction on type codes, and it is also quite fun.
I mean, this reflect, for example, it could itself be a strictly positive operator, like a container, no?
Sorry?
I mean, because the operation F here is just any operation.
Yes,
but F itself could be a strictly positive operation, so basically a container on families, right?
Yes, yes.
And then it should be okay, right? But it would be still maybe more than the super universe, or maybe not. I don't know.
I'm not sure. I'm not sure. It could be the case that super universes can already represent that. I'm not sure.
Okay.
I think probably there is like a big boost of power comes from negativity. So question, is there a large cardinal axiom corresponding to the case before Mallow? I think there is, and there is a paper, but I don't remember which one. So there is also like Rathiam about some kind of like ordinal analysis of super unit. And probably he writes about this, but I don't remember. Okay, and then it should be quite easy to see that a Mallow universe can express everything which the super universe can express, because you can always just pick this operator to be some constant family, right? And if you pick it to be a constant operation on families, then you get back the reflection principle of super universes. But you can do much more. Yeah.
But wasn't Tony's point is that Mahlo corresponds to induction recursion exactly, or?
Okay, so let's go to induction recursion now. So I think, I'm not completely sure, but this is my reading of at least like the skimming of the papers about semantics of induction recursion, is that IR is at least as strong as Mallow, but the upper bound is not known precisely.
But but it could be just as strong, or what?
It could be just as strong. I think no, not really, because there is also, so there is something which is an autonomous Mallow, is also IR definable, but stronger than Mallow.
Okay.
But then the question is then, is autonomous Mallow exactly the strength of IR? And I think that this is not known. So IR is somewhere around this autonomous Mallow, but there is no proof that it is exactly autonomous Mallow. And then, so if you go like in increasing strength, so we have Mallow, autonomous Mallow, a large induction recursion, and then we have this pi3 reflecting universe, and all of these works are by Zetzel. And it is also not known how this pi3 reflecting universe relates to large induction recursion. So here, this is kind of like already around like the limit of constructive predicative mathematics. And but I think it's very interesting that IR is, I mean, the specification of IR codes is not that simple. So like it's a pretty involved specification, like what is an inductive recursive type. And we also know that the strength of IR is also like very large. But at the same time, IR seems to be just pretty convenient feature in a programming language and a proof assistant. I mean, so like despite of its strength, it is still quite convenient to use. And it is definitely, IR is much more convenient to use than just having a Mallow universe or super universe. Because like in the Mallow universe and in the super universe, it's much simpler to specify what the super universe and the Mallow universe is, but it's less convenient to use because everything has to go through these like deflection principles.
But I think it's not so difficult to specify induction recursion explicitly, right? It's basically because you can actually, I mean, you can formulate small induction recursion, right, where you increase the universe. And then you have a resizing axiom, which basically says if this, the definable induction recursion, which gets you into the, I mean, by using the usual encoding, right, the inverse image encoding, which gets you in the next universe. But if the parameters, I mean, are functional, then you downsize the universe. It's like a resizing axiom.
Mm-hmm. So Thorsten, do you know that this is possible, or is this just a suggestion?
I had I think I had a discussion with Christian. We looked at this, but I mean that was on the whiteboard. So yeah, I have to try to remember, and maybe I'm misremembering it. So
yeah, I'm not sure that it is possible because maybe like like you cannot disentangle a large inductive recursive definition because you already need the EL when you try to define
I mean, you can turn, I mean, a small induction recursion, right, is reducible.
Yes, I know.
Yeah.
So
the whole thing is that with proper, I mean, large IR is what you get. You sort of pull the universe down, right? You just say, okay, this is actually in universe 1, but now I'm just declaring it to be in universe 0, right? So that's what I'm saying.
With small IR, it works that you have something which lives in like universe 1, and then you can give a small IR definition which lives in universe 0, but which is equivalent to the other one.
Yeah.
But this only works with small IR. It doesn't work with the general.
No, okay, but it does work for large IR. The only
no.
It
does not work.
You get a universe which is 1 too big.
Yes, and that's the reason why it doesn't work.
No, but that's what I'm saying. I mean, I'm saying that IR is a resizing axiom for this, which says, okay, this thing, which is just constructed, which is just a normal inductive definition, which lives in universe 1, is now we just decide it lives in universe 0.
Yeah, okay. I'm not sure.
So do you say that basically for any index type indexed by set, you say that it won't live in set 1 but in set 0, and this is the same as having IR?
That would be inconsistent.
No, that's not. I mean, no, you take this you take the inverse image encoding of IR, right? And now you get in general you get the type which is one universe higher, right?
Yeah, but I claim that there is no, so for general IR types, there is no inverse image decoding. So we need to have the resizing principle mutually. So already we need the resizing principle just to write down the inverse image representation.
I don't understand.
So okay, I can give some intuitive explanation. So for example, take the superuniverse, which is a special case of IR.
Yes.
And you can see that with IR we can send every family to a family, and that's why we can iterate this. But with inverse images, every time we do a reflect, we have a universe level bump. So there is it's not possible to do an iteration. We can only do an iterated reflection if we have an external universe hierarchy, but not in an arbitrary way. And that's why, so to be able to do an inverse image definition for an IR type, at the same time we need the resizing principle that we are defining the inverse image version.
Okay. I don't know. I have to think about this. So, but I try to.
But then the full resizing principle, at the same time makes it inconsistent. So that's.
No. The full resizing principle just says so. Okay. Anyway, I'll think about it. I have to go as well, and I have to say it was really very, very. I think I've learned a lot today, or partially remembered things I've forgotten, and maybe learned things I never really properly understood. So I'm really, it was a really interesting talk. I hope you make this file available, because I think I'm going to.
Yeah, I will make it available.
But anyway, I have to go because we have a meeting quite soon. I'm going to maybe recover a little bit. But yeah, thank you very much.
Yeah, thank you.
Okay, so now that people are leaving, so should we finish? I can maybe summarize like other stuff that I wanted to talk about.
Yes, just say what else you wanted to say, and then we can.
Some other stuff. Well, Paolo thought it was ending.
But yeah.
But I mean, since
it will end very soon.
Or maybe I can just do some explanation because it is recorded, so the people who are leaving can maybe just look at it if they want. So should we do that? So we go until 2 p.m. and I just try to talk about this as well.
Yeah, it's okay with me.
Okay. So the other stuff would be, okay, we want to use IR, or not necessarily IR. We just want to model like transfinite level polymorphic, whatever. Like all of these level features in type theory. And using whatever. So maybe it is possible to do this with only superuniverses, or maybe it's not. But we just want to give some model for this. And but at this point, so I think we might ask the question: so why have fancy universe features if we can just add IR? So my FSCT paper just proves that fancy universe features can be modeled with just using IR. So the question is, why have the fancy universe features if we can only IR? And the answer to this is that IR allows you to define universes in a deeply embedded way. But the deep embeddings are not as convenient to use as like native language features. So if I'm using the IR, then I have to do some propositional proofs, and I have to transport over those proofs, and I have like a heavyweight representation of types and type codes in the universe. But if I have like the native features, then I can also have some like level inference, some maybe implicit coercions between different types. So this like a coercive subtyping, or maybe it's just a normal subtyping, and maybe I can also have like, so it's more convenient. In general, so the motivation is that the fancy features should be justified using something which is simpler in terms of specification, but which is less convenient to use. I mean, it's the same thing as like having inductive families versus just W types and IP types. So one is easier to specify, but the other one is more convenient to use. So we want to prove that inductive families can be justified with W types and IP types. Okay, and but here there is an issue. Okay, so there is an issue. And the issue is that so we want to pick any ordinal alpha, and we want to have a universe hierarchy. So we want a cumulative hierarchy indexed by all the ordinals which are smaller than alpha. But for this cumulative hierarchy to work, we want that the U. So whenever I have an I smaller than j, so I'm just starting to use I and j for levels, then the UI should be recursive subuniverse of uj. And then so like in the like the syntax of this algebraic cumulative universe is, and also the syntax of Agda, which is not cumulative, but we already have these liftings. So an embedding from UI to UJ is called a lift, and what we want is that lift should preserve type formers and also term formers. And this is exactly what a recursive subuniverse means. Okay, but what's the problem? So the problem is that using super or Mallow, it's not known. I mean, in the papers that I read, there is no demonstration that you can combine transfinite universes with recursive subuniverses. And I can also do some intuitive demonstration. So, or not demonstration, just some short intuitive explanation. So the reason is that in order to do a recursive subuniverse, so you can see here that I gave one example for a recursive subuniverse. So this is like the Gröthendieck universe when there is the recursive embedding from the small u to the large u. And you can see that this recursive embedding is defined by recursion. That's why it's called recursive. And if you move on to the super, then it's not recursive anymore. But the thing is that if you have like a countable hierarchy, then all of the liftings that you have to do can be defined essentially just step by step. Because like if you have a UI and if you have a UJ, so a recursive embedding. So if you have a UI and you have a UJ and maybe internally to a super universe, let's call it maybe small u, because this is just some kind of subuniverse of the super universe, then the recursive embedding is actually, it's fine if I and j are finite. So this is okay if I and j are finite, because then there is a finite difference between I and j. and we can just do induction on the difference between I and j, and just do a stepwise embedding, just embed until we get there, right? But it doesn't work if we have something like an ui, and I is finite, and I want to embed it into a u omega. Because then we cannot do an embedding in an iterated way, right? So there is nothing to do, like we cannot reduce it into a finite number of like recursive embedding steps. Okay, so what's the solution? So my solution is just to not use super and Mallow, just to give a very direct inductive recursive definition for a universe which is indexed by an arbitrary ordinal number. And then we can just go to the formalization for the paper. Okay, so what we say is that we have any set with a well-funded transitive relation. So it's actually, I mean, it's not necessarily even an ordinal number, because it is not necessarily totally ordered. It's just any set with a proof relevant ordering, which is transitive and which is well-funded. So if I want to be very fancy about how to specify the structure, that I could also say that this is like a thin inverse semi-category or something like that. But it would be like it would sound a bit stupid in my opinion. And in principle, we could just move to inverse categories and everything would still work, but it would not be very useful because all of the extra, like the proof relevant morphisms and the identity morphisms, are completely unnecessarily in the semantics that we give here. Okay, so we have this higher universe, and then we just give a direct definition. So we say that there is a universe operator which is called this UIR and ELIR, but the universe operator is parameterized by kind of an interpretation of an initial segment of the level structure. So the level structure, you can view it as kind of an ordinal, and every initial segment of an ordinal is still an ordinal, and you can view it as basically a semantic interpretation for the initial segment of this level structure, and then it works very nicely because I can say that I have this U prime code, which works by, so we already have this I, which acts like the current level, and then we say that we have a code. So in the I universe, we have a code for every universe which is smaller than I. So you can see here, like for every j, such that j is smaller than I, we have a code, but this code lives in level I, right? And then we can define EL, and then what happens is that whenever we want to interpret a code for any universe, we just use the semantic interpretation of the initial segment of the level structure. So we get a set for every j which is smaller than I. So we just use this semantic function here. And now, so this also works kind of as a universe operator, and we can iterate it, and we can just do induction on the well-fundedness of levels. So for every level, we get this like accessibility witness, and then we can just do induction on this accessibility witness, and essentially kind of by induction start from the small j's, and at every step of the iteration, we are building up a larger and larger semantic universe, and in the whole definition, we give a semantic interpretation for every level in the level structure. Okay, so this is kind of the definition. So this is like a semantics for every initial segment. So whenever I have an I and a j such that the j is smaller than I want to get a set, and it's defined by recursion on the accessibility. So this u smaller is defined to be just just a set of inductive recursive codes. And if I do this definition, then I can just define like the whole U and EL like indexed over arbitrary levels by just using the fact that everything is well-founded. So I mean levels are well-founded. So every concrete level is accessible. So I can just pass this accessibility witness in this U and EL. Okay, and the point here is that like there is no inductive embedding from a smaller universe to a larger universe, because I only have this U prime here. So because there is no inductive embedding, then like the subuniverse embeddings have to be defined recursively, but it is possible to do it, and it does not matter what this relation is, because I can just do recursion. So I can just define this lifting function, and then it does the recursion and the type codes. And the only interesting thing which happens is that whenever I want to lift an U prime, I can just rely on the transitivity of the ordering of levels. And then I can also prove that this lifting preserves the elements. Right? So, and if we do this, then we can actually just model all the fancy type theoretic features. Because we have these universes, you can index it by whatever, and then you also have these very strict lifting properties, which model all the cumulativity features that we want. And if you have this, then it turns out that actually you can just say that levels are an internal type, and it doesn't make a whole lot of difference from the perspective of doing an inductive recursive semantics for some type theory. Okay, that's it. So any questions or comments? I mean, I've already talked about this stuff, but in a slightly different presentation and formalization. And I was talking about these universe levels.
So in the internal definition of levels, what's the what can you do with levels? What's the interface? Is it basically this record and that's it?
And I can also just go into that file.
Or in the model, yeah.
So in the paper, the way this is done, it would always work to say that, okay, levels are identified with some type and just baked into the specification of this theory. I mean, it would always work. But I did not want to do that because it's not very modular, because then I cannot talk about like lots of different versions of this in a more generic way. So in the paper, what I use is that so I kind of gave a generic definition of a type theory with internal levels, but which leaves it open, like what is the structure of levels? So we just know, we can look at it. So we have like con, sub, whatever, and we have levels, and levels can depend on context. And we have like level orderings, and level orderings can also depend on context, and it depends on two levels. So these are kind of dependent levels. And then we have like substitution for levels and level orderings, and we also have like the usual CWF structure, and we also have this lifting structure. So we have the lifting operation on types and terms, and lifting is cumulative, and we also have universes, and we also have basic type formers. So we have all this structure, but at this point we know nothing about the internal structure of levels. We only know that it is specified that there is a sort of levels and there is a sort of level orderings. And but if you have this specification, then we can say that that there are some level reflection principles. So, for example, I can say that there is an internal type. I can just pick any internal type in the syntax of this previous theory and add the reflection rule, which says that that levels in some context gamma are the same or isomorphic as terms of this internal type of levels. And I can do the same thing for this LT as well, but I haven't formalized everything in this file. It's pretty much just a sketch. Yeah. So the way it works is that there is already like kind of syntactic structure for internal levels is available, and on the top of that you can just assume that levels are the same as some internal type. And if you assume it, then you can just do induction on levels. Like if you assume that levels are natural numbers, you just do induction on natural numbers. Of course, we still have to show that it is consistent to assume that that levels are natural numbers or any other type former, but that's pretty easy to do, because you can always just start by picking a level structure in the meta theory such that it's obvious that there is an internal representation using basic type formers for that level structure. So was that clear to some extent? The point is that like we have a sort of levels which depend on context. We have a sort of level orderings and lifting operations and universes. And on the top of this, we can just assume that this is isomorphic to any internal type, and this is also isomorphic to any internal relation. And I tried to make this even more generic, like trying to make it more precise, but this was the best that I was able to do. So I tried to do this by using some kind of more abstract presentation, but I was not able to make it work because like there is some pretty tricky like circularity in trying to justify these things, because everything is already indexed by levels. So first you have to give a model for something without the level reflection, but then you have to extend it to a model which has the level reflection, but already everything depends on levels in the original model and so on. So it becomes a bit confusing, and this was the best that I was able to do. And I think it's fine. I mean.
Okay. Shall we finish, or do we have to discuss anything else?
I stopped the recording anyway, in any case.